Hey, welcome to the Moberly Science Physics First ninth grade acceleration unit review guide. It's kind of a mouthful, but this is for the freshmen in Physics First at Moberly. And we are finishing up our acceleration unit, and for the goals of this video, we want to determine what is velocity and compare it to speed, what is acceleration, identify all four types of position versus time graph. That means, is it speeding up in a positive direction? Is it slowing down in a positive direction, speeding up in a negative direction, and slowing down in a negative direction? And then transfer those to the velocity versus time graphs. Then we want to calculate instantaneous velocity using the average speed and the middle point. And then we want to calculate acceleration, and then we want to calculate distance. Now, in order to do that, you need to be first aware of the process of solving all of these problems and keeping them all in order. And hopefully when we get to that, we'll show you precisely how to do that without getting confused. So we're beginning the review guide, so if you could please get us a review guide while we do this and follow along. Now, if you're doing this at home, pause when you need to or skip ahead when you need to. This video is going to be kind of long, and depending on your speed, depending on how much you know coming into this video, you can either pause or skip ahead, and that's up to you. So first and foremost, we're going to get into accelerated motion. And as it discusses right here, we're going to have this example, and to read it, the graph to the right represents a motion of a fish swimming in a tank. And so first things we need to notice is that this is going to be a position versus time graph. And so we have position over here, and then we have time in seconds over here. This is not a velocity versus time graph, which means that the motion that we're looking at is ultimately going to be looking at its speed. So those things to keep in mind. Now, we're going to get to the questions, but before we even get to the questions, there's some things that you should know going in right off the bat. So we have these 3 points here, A, B, C, and then these other three, D, E, F. And what's going to ask you to do is analyze these motions. And first off, we have the home or starting position is here. So anytime it moves up over here, anytime it goes away from the home or starting position, that's going to be a positive direction. Now, my class knows this pretty well, and I'm sure your class does as well, that anytime you go away from your starting, that's a positive. Anytime you go back towards your starting place, that's going to be a negative direction. And those are the things to key in on. Now, if you remember that the slope indicates how fast you are going. And so a fast slope indicates that you're going pretty fast. A medium slope indicates you're going slower, and then of course a flat line indicates there's no speed at all, or not no speed, no motion whatsoever. Again, this is not a velocity versus time graph. This is a distance versus time graph. So this is no motion. No matter how much time goes along, you're not moving. So let's go back to these questions now that we have that covered. At what points on the graph above is the fish moving the slowest, and how do you know? So let's answer this right here. Well, what's the slowest possible speed? The slowest possible speed is 0. So what we want to see is when are they moving at 0 meters per second? So 0 meters per second. When do I see the flattest positions? Well, I see the flattest position here at this crest here at B. It's moving 0 meters per second. And I see the flattest position here at position E, moving 0 meters per second. So how do I know? So it's going to be B and E, and the reason being because they have a slope of 0. They have a slope of 0. So slope equals 0. Now I want you to probably write it a little bit neater on your own paper, maybe using full sentences. Over what time intervals does again, specifically it says time intervals. Over what time intervals on the graph above is the fish speeding up? And how do you know? So we're looking over here in time intervals here. So from 0 to 2 is going to be from the start to B. From 2 to 4 is from B to D. And from 4 to 6 is from D to E. And then 6 to 8 is going to be E to F. So we're going to focus and key in on those. So the first part is, when is the fish speeding up? So the question is, when is my angle going from flat to sharp. So when am I going from flat to sharp? Now I can go flat to sharp positive or flat to sharp negative. It doesn't matter as long as I'm getting from flat to sharp. And so let's look at any time. And a good way to look at it is anytime I go into my zero slope, that is slowing down. And anytime I'm leaving my zero slope, that is speeding up. So where am I leaving my zero slope? Well, from 2 to D, B to C, and go on into D, I am getting faster. So intervals 2 to 4 seconds, I'm getting faster. And then intervals 6 to 8, I'm getting faster. Why? Because I come over here, I'm flattening out. I'm flattening out and I'm slowing down. And here I'm getting faster. Here I'm flattening out, so I'm slowing in this area. And from this area over here, I'm getting faster from E to F. So over what time intervals on the graph is the fish speeding up? And how do you know? The time intervals are from 2 to 4 seconds, and then from 6 to 8 seconds. And then how do we know? The angle goes from flat to sharp. Over what time intervals, letter C, over what time intervals on the graph above is the fish slowing down, and how do you know? Well, I kind of just covered that here, so there's no way to iterate that point. Again, I'm slowing down if I'm going to a flat, and I'm speeding up if I'm going from flat to sharp. So if speeding up is going from flat to sharp, then slowing down is going from sharp to flat. So here I am, my angle is flattening out, my angle is flattening out. So I would say from 0 to 2 seconds, and then from 4 to 6 seconds is when my angles are flattening out. And so it's going from sharp to flat. Now any way you want to word that, as long as you understand that the line which represents slope, distance over time, this is distance over here and then time on the bottom, that's going to get me to a 0 here, and this is going to get me to a 0 there. Every time it goes towards my 0, that's a slow speed. At what points on the graph is the fish changing direction? Now, in my class, the first thing I always talk about when we're trying to do these problems where we're looking at graphs and figuring out, trying to draw the qualitative graphs of speeding up, slowing down, positive or negative, I always ask them to recognize if it's going in a positive or negative direction first. And as we mentioned at the beginning of this video, anytime it's going away from the 0, that's a positive direction, and anytime it's going back to 0, that's a negative direction. Just like those practice problems where we talked about going from home. We had Dan going from home, we had Dalton going from home, and we had Ed going from home. Those are all positive because they were going away from the 0. Now, when Stephanie and Hawk went back towards home, that was all negative direction. And I hope you remember that from your homework assignments. So let's go. At what points on the graph above is the fish changing directions? Is it asking for time intervals now? It's not. So be cognizant of the fact of what it's asking for when it's asking for time intervals and when it's asking for letter intervals. So at what point on the graph is the fish changing directions? When do we see it going from one to the next? Well, this is going up in a positive, and then it stops here. That's what a slope of 0 means, that it stops and then it goes back down. So we see from B to C, it's going from positive to negative. And then it keeps going on a negative direction. D to F, it's slowing down. D to E, I apologize. D to E is slowing down. And then from E to F, it goes back from a negative direction to a positive direction. Letter E, finally, over what time interval, again, is asking for time. Over what time interval does the fish appear to be traveling at a constant speed? Now, this is one of the questions that you should be pretty familiar with. That's kind of the entire purpose of this whole entire unit, was for you to recognize changing speed, accelerating speed, versus constant motion. Now, just to review, if we're looking at a distance versus time graph, distance versus time. So I'm going to have x, or distance, on the side here, and time in seconds. In my class, I usually focus on distance on the side here so we don't get confused. Because while this is saying x as in position here, so in your graphs you'll see this is position, and this is going to be time. If I have a flat line, that means no motion. If I have a diagonal line, that means constant motion. Constant motion. And then if I have, at any point in time, I have a curve of any kind, it doesn't matter the curve. It could be negative speeding up, it could be negative slowing down, it could be positive speeding up, positive slowing down. If at any point in time I have a curve here, that is changing speed or changing a velocity. So the question is asking, over what time interval does the fish appear to be traveling at a constant speed? So when is there a straight diagonal line, whether up or down? So let's go look through here. Okay, we have 0 to 2 seconds, it's slowing down. That's a curve there. From 2 to 4 seconds, or it really, for 2 to 4 seconds, you have this from the C to D range. That's the only time I see a constant line here. That's the only time I don't see really a big curve. So to the end of the question, it's going to be 2 to 4 seconds. And the reasoning why? It's a diagonal line. That's the reason. Okay, let's go to the next page. You should finish that up. If you need to pause and go back and go over this some more, please feel free to do so. And I will leave those there. Next, we're getting to the calculation area of this. To preface this, I want to go over a couple of things off to the side here, and I'm gonna illustrate some ideas. When we were doing calculations, we here focus on the guess method, and the guess method isn't special. All the guess method is identifying your parts, plugging them into a known equation, and then solving and being consistent with the methodology every single time. So in my classes, one thing I have them do is at every chance I want them to box any variables they see. Put them in a box and label them with a specific variable to see what we have. So I'm going to do that same method here, and I'm going to put it in a guess format or guess boxes, and you work with me as I do this. So question number 2 asks, a stunt driver is testing the airbags of a new model car. He first drives the car at a constant speed of 25 meters per second for a total of 100 meters. 50 meters from the wall, he applies the brakes and accelerates to a stop just before he reaches the wall. Now I want to focus on what that word accelerate means right here, and then we'll go on to this graph. You notice right here that it says it accelerates. And I want you to notice that acceleration is a general term for any time velocity changes. Any time the velocity changes. It doesn't necessarily have to be speeding up. Acceleration is just a general term any time velocity has changed. And velocity consists of 2 ideas. So velocity is both speed and direction. So anytime I alter speed by slowing down, slowing, or speeding, I've accelerated. So here it goes from 25 meters per second, and then he applies the brakes and comes to a stop. So he was originally going 25 meters per second, and then he stopped. That's a slowing down. That is a form of acceleration. The other way you can accelerate is by changing direction. Remember, acceleration is velocity is a vector. Velocity has both direction and magnitude. So we have direction and then magnitude. And if you ever change either one of those, you've accelerated. So on our questions, the last 2 quizzes, we've had the question of which is acceleration? Going around a track at a constant speed? Well, did we change direction? Absolutely. So therefore, there's an acceleration. speeding up to slowing down to a stop sign. So I'm going here and I'm going fast, and I see this big stop sign. I'm going fast and I slow down, and I stop. Well, did I change my speed? Absolutely, I've accelerated. And then the question always was asked about the dogs running at the same speed. Now that doesn't look very pretty. Those arrows are supposed to represent speed in a straight line. So, was the direction change with the dog running at the same speed in the straight line? No, direction didn't change, and the speed didn't change. So therefore, there was no acceleration. Just to clear on that, I hope we've now got the terms of velocity. Velocity is a vector, which means it has both direction and magnitude. So let's get ready to start answering these questions for here. Now, let's go see if there's any calculations involved in here. I've got numbers at 25 meters per second, so that's going to be velocity, and a distance of 100 meters, that's going to be distance, and stop, that's also velocity of 0 meters per second. Then it says, sketch a qualitative position versus time graph and a velocity versus time graph. Label your axes and include the units. So if this asks you on the test, you have a couple points you're going to have to look at. You're going to have to draw the graph. Are there any numbers? No, there's no numbers. But you will have to label your axes. And that means on our y-axis, the one that goes up and down, this is going to be position versus time. It tells you position. It says label your axes and include units. Well, we're going to go meters because we always deal with meters. And then time on the bottom. And we always do seconds. And then velocity versus time. Well, what is velocity over time? Same thing. It's velocity. And by now, you need to have all of our units memorized. There's no exception for not having these units memorized by now. They've been on all your work problems. They've been on my board. I'm sure they've been on the other teachers' boards. You need to have them memorized. And this is going to be meters per second. And then the time is going to be in T seconds. Time in seconds. So we got those taken care of. Now let's go look at this. Is it in a positive or negative direction first? That's what we got to look at. So Stark drives the car at a constant speed of 25 meters per second for a total of 100 meters, 50 meters from a wall. He applies the brakes and accelerates to a stop just before he reaches the wall. So he's leaving his starting point. When you go away from your zero, that's a positive direction. Now he drives at a constant speed. Remember, what does constant mean over here? It means I'm going diagonally. I'm not curving. So you'd better not have a curve when you begin this. You better not have a curve. So we go here. He first drives at a constant speed of 25 meters per second for a total of 100 meters. 50 meters for the wall, he applies the brake and accelerates to a stop. So the first beginning of it better be constant, and then the second must be an acceleration of some form. Well, accelerates to a stop. So let's go ahead and show the first part of it. I got a constant speed. Constant speed for about 100 meters. And again, do I have any actual data points? No, I don't. So it's all qualitative. And then what happens? He accelerates, i.e. slows down. And that means he's going to start flattening out here. He's going to start flattening out here. And then he comes to a stop. So the first part, it's a constant speed here. I got a constant speed on my first part, and then I start slowing down. That means I was going fast here, and then I went slow at the end. Fast to slow is a slowing down, and it is that simple. I'm not trying to make something complicated simple. It is really that simple. Now let's go over to the velocity versus time graph. How do I transfer this? And again, what I ask my students is, first and foremost, let's look at the direction. Is it going to be in the top quadrant or the bottom quadrant? And what I mean is, come over and look at this graph over here. Normally we have two quadrants for our velocity versus time graph. The positive quadrant and then the negative quadrant. If I'm ever going in a positive direction, I'm going to be in this quadrant. It doesn't matter if I'm speeding up or slowing down. If I'm ever going in a negative direction, I'm going to be in the bottom quadrant. It doesn't matter if I'm speeding up or slowing down. It doesn't matter. But we only have one quadrant over here, so what is that there to tell us? Well, that's there to tell us that we are going to be in the positive quadrant because we're in a positive direction. Now, one thing that I warn my students that a position versus time graph and a velocity versus time graph, the lines don't mean the same thing. So as you remember, let's go back over here. As you remember,
on a distance versus time graph, or position versus time graph, a diagonal line, or I'm sorry, a flat line meant no motion, a diagonal line meant constant motion, and a curve meant changing motion. They do not mean the same thing on here, and I'm going to juxtapose these right beside each other. Juxtaposition means whenever two things are side by side. So let's get these side by side here. So I have a distance, a velocity versus time, and I'm going to put my quadrants here. So if I am showing, let's go to no motion first. If I am showing no motion, then the no motion is 0 meters per second, and that's right here at 0 meters per second. And the whole time, so this is time right here, this is velocity meters per second. As time is going forward, my motion isn't changing, so there's just nothing there. There's nothing to show except I'm at this position the whole time. Now, if I have a constant motion means the same speed. It doesn't matter positive or negative. It means my speed is the same. So what does constant motion represent? It means a flat line on this one. So remember, a constant motion on a distance versus time is a diagonal, but a constant motion on a velocity versus time graph is a flat line. And then finally, on a accelerating or changing motion graph, it's going to be a diagonal line. So it's going to be if it's speeding up in a positive direction, that means I'm getting away from the 0 meters per second. That means I'm going up. That is speeding in a positive. Now, if I'm slowing down in a positive, I'm going towards my 0 meters per second. So here I am going towards my 0 meters per second. That is slowing in a negative. And let's go there. Anytime, doesn't matter positive or negative, if I'm going towards the 0 line, that is slowing down. So which is the way I explained to my students was, when am I going faster? 70 miles per hour towards Columbia, or 70 miles an hour going away from Columbia? Doesn't matter. All it is direction. So same thing here. If I am going away from the 0 line here in a negative, that is going to be speeding. Negative. If I go towards the 0 line, that is slowing. Negative. By the way, I hope I put positive over there. I hope that helps. So with that in mind, go back and look at these two things. And if you need to pause and rewind to go look at that, please do so. Let's go look at what we have to do. So it says, sketch the velocity versus time graph. So over here, we see it's going at a constant speed. And remember, what does constant mean on a velocity versus time graph? It means that they are going flat line here. So I'm going to draw a flat line first. So I got a flat line. Let me magnify this. And then it accelerates to a stop. Remember, this is 0 meters per second, and that's what stop is. So you're going towards the stop. So it's a diagonal line towards the stop. Okay? So here I am, constant motion at first, on a distance versus time graph, and then I am accelerating and by slowing down. So fast to slow in a positive direction. Here I am, constant motion, flat line, and then slowing down, going towards my 0 line. Okay. Next, let's look at Marvin's motorcycle can accelerate when he starts from a stop to 12 meters per second in 6 seconds. We need to first calculate it's asking us to calculate his acceleration. And before I do any of this, I'm going to erase this, get this out of the way, because I want to focus on, get everything else out of the way, and I'm going to go over the process. And one thing in my class I stress is, learning how to do a problem is good. But learning the process of solving any problem is even better. And the guess method is there to help us do that. It's there to help us organize our thoughts. And if you don't like it, just learn to organize your thoughts and accept that. So here, Marvin's motorcycle can accelerate when he starts from a stop to 12 meters per second in 6 seconds. Calculate his acceleration. One thing I want you to do, and my kids especially, I've focused on this and focused on this. I want you to start boxing all the variables you see from a stop. From a stop. Well, what does stop mean? Stop means 0 meters per second, velocity terms. And he starts from a stop. So is that my initial or final velocity? Well, that's my initial. I'm going to call that v sub I. To 12 meters per second. Well, what's that going to be? A v sub f, my final velocity, in 6 seconds. So I'm going to come over here. That's going to be my t sub f. Now, my students automatically know, almost always, unless we give it to you otherwise, your t sub I is going to equal 0 seconds. So your t sub I is going to equal 0 seconds. And that was a lot of times the same case for our velocity versus time. And the question is, why? Well, when you get your stopwatch, what is it the time always begin on? 0 seconds. So doing the guess method here, we're given a list of variables, and I've stressed on my kids write them off to the side. So I'll go ahead and write the G for the guess box. And that's going to be v sub I equals v sub f equals t sub I equals and t sub f equals. And that's going to be 0 meters per second, 12 meters per second. I can make this a little bit bigger. Let's erase this so it can be more organized. I'm sorry for those who are hyper organized and hyper pretty on your writing. That is not me, as my students can testify. And 12 meters per second. And then time is going to be t sub I is 0 seconds, and t sub f is 6 seconds. So let's come over here and plug it into, what's our unknown variable? Well, it says to calculate acceleration. That's what we're looking for. So a equals question mark, and then we plug in our equation. And our equation is going to equal a equals v sub f minus v sub I over t sub f minus t sub I. How do you know that equation? Because you're given it. It'll be on the board or on a slip of paper that you'll be given. Then we substitute, and our a is going to equal 12 meters per second minus 0 meters per second over 6 seconds minus 0 seconds. And when I get done, my answer is going to equal 2 meters per second squared. Okay. Now, I'm going to come over here and I'm going to focus on that. Some of you may not know how to calculate for the unit and how do you get the correct units. That's kind of a non-starter. I would love for you to be able to calculate that and show how when you keep, change, flip, and how you get these units, but it's not the end-all be-all. You need to have a couple things memorized. One, time is always going to be seconds. Distance is always going to be meters. Velocity or speed, and you should have that down by now, is always going to equal meters per second. And then acceleration is always going to equal meters per second squared. Just have that memorized. So we got our answer at 2 meters per second squared. Fantastic. Now, what is the distance of the car after 3 seconds? So let's erase some of the problems, and hopefully you'll have more space so you'll be more organized. I'm going to erase this stuff get this out of my way. We're going to keep some of our things. I'm going to put acceleration equals 2 meters per second squared, because we have another distance equation. If y'all need help remembering, we're going to have a list of equations, and one of the equations we're going to have there is going to be distance equals, let's get a different pen so we can see this. Distance equals 1/2 AT squared. And to remind the students who struggle, whenever I have letters next to each other, it implies multiplication. It doesn't have to come out and say it, it implies. This is going to be 1/2 times A times T squared. You have to square the T before you can multiply by anything. This is PEMDAS 101. So that's my equation I'm going to be using. Am I given my variables? I know that's for distance. I know I'm going to need A, and I know I'm going to need T. Am I given those? Let's go look back in the question. We're given time here at 6 seconds, and we calculated A. So what am I warning you? I'm warning the classes that on the test, you're going to have to calculate acceleration, and then probably after you calculate acceleration, you're going to have to use that newfound acceleration to calculate the distance traveled. And so now let's plug this in. So my A, using the guess method, my A equals 2 meters per second squared, and my T equals 6 seconds. My U is distance, and my E is D equals 1/2 A T squared. I'm going to plug it in. So it's going to be D equals 1/2 times 2 meters per second squared times, and here's the key, you need to understand this, 6 seconds. All of that is squared. All of that is squared. So now let's solve it. Now, using PEMDAS, you understand, you take care of your parentheses and exponents first. Well, the only thing that is parentheses is the exponent, so that's one and the same. Now, you got to solve that first. And if you want to, you can calculate 1/2 times 2 at the same time. It doesn't really matter. So I'm going to solve it. D equals 1 meters per second squared times, and what is 6 seconds squared? 6 seconds squared is going to be 36 seconds squared. So when you get done with this, you're going to just plug this, multiply those two numbers, and if you can't calculate these units, you don't know what units this is going to be in, just memorize it. It's going to be distance, and distance is going to be meters. So now, when I get done, it's going to be 36 meters. So if we look, did I show my work? That's 1 out of 3 points. Did I get my correct answer? That's my 2nd out of 3 points. And did I show the proper units? That's my 3 out of 3 points. You're going to have to be able to do that. Now, using this information, generate a table of velocity and time data for the 6-second period. So we're going to have to draw a graph of velocity versus time. That means you will have 8 things that you need to cover. 8 things. First is the title. Did we get the title? And the title's got to be the effect of IV on DV. Now, if you are like some students and you struggle to remember which one's IV, which one's DV, to help you, look at this graph. This is always going to be your X. This is going to be your Y. Your X is going to be your independent variable, and your Y is going to be your dependent variable. So X is independent, and Y is dependent variable. And then you just write the effect of, well, what is T? The effect of time on, let's reverse that, time on velocity. Okay. Now, that's taken care of. What's the next thing? So that's 1 out of my 8 points. Let's get my proper label and units. When I get done with labels and units, those are a total of 4 extra points. So let's make sure we get those down. So the side is going to be velocity. It's going to be in meters per second. The the bottom is going to be time in seconds. Now it's it's not qualitative, so you have to generate the whole thing. Now that means, so far that's 1 point for my title, 2 points for my label and units, another 2 points for my label and units. That's going to be a total of 5 points so far. So that's 5 out of my 8 points. Now I need to get my proper scale. In order to figure out my proper scale, I need to actually finish this graph. And so let's finish this right here. At 0, I'm going to have a velocity of 0. But let's go back to this right here. My acceleration, as we said over here, was going to be 2 meters per second squared. Well, what number is there? That's really 1. So 2 meters per second per 1 second. So I went 2 meters per second in my first second. 2 meters per second in my first second. So at 2 seconds, where do you think I'm going to go? I'm going to go 4 meters per second. This is just a pattern. At 3 seconds, I'm going to go 6 meters per second. At 4 seconds, I'm going to go 8 meters per second. 5 seconds is 10 meters per second. And 6 is going to be 12 meters per second. Let's go look up there. Is that what we had over here at 12 meters per second? It was in 6 seconds? Absolutely. So now that we have this filled out, we can go ahead and make our scales. Now the problem here is that I only have 1, 2, 3, 4, 5 spots available for my velocity, and I have 10 available for my times. Well, I need to get up to 12, and it doesn't look like I'm going to be able to do that, so I'm just going to just keep it down to 10. It's not going to be a backbreaker here. So I'm just going to go by 2s. So this is, of course, 0 meters per second. Now remember the rule of scale is that you can't skip. You have to have the same intervals. So 2, 4, 6, 8, 10. And over here it's going to be, let's change our pins up so we can see this. 1, 2, 3, 4, 5, 6, 7. Okay, so let's draw our points. First it's going to be 0, 0, then 1 second at 2 meters per second, then 2 seconds at 4 meters per second, 3 seconds at 6 meters per second, 4 at 8, 5 at 10, and draw a graph. So that would be the correct graph. I got 1 point for my title, 2 points for my label and units, another 2 points for my label and units, 1 point for my scale, 1 point for my scale here. That's a total of 7 points, and then I drew the correct line. That's 8 of my total points. And then so we drew the graph, check. And then what does the slope of a velocity versus time graph represent? Well, this is velocity over time. What does that line represent? What equation did we have that was velocity over time? That means that slope represented acceleration. And that was on your last 2 quizzes. The question that read, what is the equation for acceleration? And it was the slope of velocity versus time. What are the units of your slope? Well, what is the units for acceleration? Have them memorized. Meters per second squared. Then is your slope positive or negative? Am I getting faster or am I getting slower? Well, I'm getting faster, which means it's a positive slope. Again, rewind this if you need to. If you don't need this, skip ahead. Complete the velocity versus time graphs from the position versus time graph. So here's our position or distance, and we need to incorporate them into our velocity versus time graph. And again, what I tell my students is, you need to look, is it first direction, and that is terrible handwriting, so let me magnify that. 1, direction. And then 2, are you speeding up, or slowing down? And that will tell you what you need to do. So is this positive or negative? This is a 0 mark, right? Is it going towards 0 or away from 0? Well, it's going towards. So that makes this negative. Now, that means you need to put it in your negative quadrant. Without exception, if you put this in your positive quadrant, you're going to get it wrong. This over here, is this positive or negative? Well, this one's in a positive direction. So that means you need to put it in this top quadrant. If you put it in another quadrant, you're wrong. Now, this one is negative first, then positive. So that means that it takes up both quadrants. Now, is it speeding up or slowing down? What I tell my students is, circle the beginning and the end. Is that fast or slow? Is that angled? Yeah, it's angled, so that's fast. Does that flatten out? Yes, it flattens out, so that's slow. That means it's slowing down over time. Well, that's slow, and this is fast. That means it's speeding up. And this is a combination of both of them. It's slowing down and then speeding back up. So what does that mean on these graphs right here? I already told you it's got to be in this quadrant. Well, remember, this line represents the 0 meters per second line. This is going towards my 0 meters per second. It's getting slower. So that means I start here, away, because we start off fast. Remember, any point away from here is fast. This is fast positive, this is fast negative. I'm fast negative, and I go towards 0. Go to the next one. I'm in the positive quadrant, and you better know that. Do I start off fast or do I start off slow? Well, I'll start off slow, and slow means here. Then I get faster. That means I go away from my 0. Now I'll put the whole thing together. Fast to slow, from slow to fast over time. Negative, then positive. So I'll start off negative, then positive, and I continue. And you can see how that's a combination of both of these, hopefully. Now, I hope that methodology prepares you. Again, direction first, and then you X out the ones that aren't available. If you have 4 boxes there, X out the ones that are not going in the right direction first. That knocks off 2 of them, and then cross off the one that's speeding up or slowing down incorrectly, and then you knock off the 3rd one, and it's process of elimination. Number 5, look at the track configuration provided below and represent the motion with 1, a qualitative graphical representation of distance versus time, or position versus time. That's what the X means. A qualitative graphical representation of velocity versus time, and then a qualitative motion diagram. Those are 3 things, and they're all qualitative, which means no numbers. Let's do distance versus time first. Now, things you need to key on. 1, 0 meters per second. That means the ball is traveling home. This is going to be a negative direction. That's going to tell you one of the most important things. That means on this graph, you're going to be going down, and on this graph, you're going to be in the 2nd quadrant. That doesn't tell me what my line is going to look like. It just tells me which direction my line is traveling on the position versus time, and then which quadrant I use on my velocity versus time. Now, second, it says that your initial velocity is going to be 10 meters per second. V sub I means 10. That means you start off fast, and you're going to stop up here because of gravity, the only thing that's working on it. This should cause you to remember our motion sensor activity with the car going up the ramp. When we did that, it slowed down. So let's go through this then. I'm going to go negative and slow. So I'm going to go start here and go down. So I'll start off fast. Before I do anything, I know I'm going to start off fast, and I'm going to end stop. So I'm just going to connect those into a line. Okay. Here's the same thing. I'm going to start off fast, which means away from my 0, and I'm going to end up stopping, going towards my 0. By the way, you should think of these right over here. We just discussed this. Look at what we did over here, and look at what we have over here. They are the exact same. And then finally, let's do the motion diagrams. And as I remind my students on the motion diagrams, you must remember that you have to put your representative line first, your reference line. So let's get my reference line here. Okay, that tells me the direction. Now it says I'm going to slow down in a negative direction, so my arrows are going to have to go the opposite direction. So here I am going in an opposite direction. Now I start off fast and get slower. So remember, the dots represent seconds. So at this first second interval, I'm fast. Second interval, I've slowed down. Slow down. You notice how the seconds are getting closer to each other? It's not that the time frames are getting shorter, that the distances between my time frame are getting shorter. So there I am. This is check, I've got my qualitative position versus time. Check, I got my distance versus time. And check, I got my motion diagram. Now let's do the last one. The graph below shows a position versus time graph for a ball as it rolls down a hill. So it's what we need to do is complete first. So 6a says complete the graph by adding the missing parts. Now there's 8 points to this. So remember, out of the 8, you have your title. Does this have a title? No. Does it have labels and units? No and no. No and no. Does it have your scale? Yes, and scale there, and then your plot. So it has only 3 out of your 8. You're going to have to put in the other 5. So let's get cracking on putting the other 5. If you want to, you can just put the scale and the units, the labels and the units to the side or to the tops. So first off, it's a position versus time graph. That means it's going to be the effect of IV on DV, which IV is your X, and DV, so this is I, this is D. So whatever your I goes first, and whatever your X-axis goes first, and your Y-axis goes second for the naming. So let's get their name going. So it's going to be the effect of time on position. And this is going to be, again, my class uses distance. Others uses X. I'm going to put them both. This is going to be distance in meters and or position in meters. This is going to be time in seconds. Okay. So I've got 1, 2, 3, 4, 5 things I fixed. What is the slope of a position versus time? Well, my position is meters. My time here, what is distance over time? What is distance over, let's make that look prettier. Distance over time. You see how I'll put that over the line? That equals velocity. So what does that represent? Velocity. So let's make sure we don't forget that. Then what is the instantaneous velocity of the ball at 1 second? This was on our quiz, so you should not forget this. At 1 second. My class has a set of steps to do. 1, we have to first recognize that when it's asking for instantaneous velocity, we're going to have to find the average and make our instantaneous velocity the point in the middle. So how do I find the instantaneous velocity at 1 second? On the last 2 quizzes, we've had a question that says, if you find the average speed, then you have found the instantaneous speed where? And the answer has always been the point in the middle. So let's reverse that. So if you have average speed, comma, then you have instantaneous speed. Only at the midpoint. So if I want to find this at 1 second, I have to reverse that. I have to find if I want to find the midpoint, or if I have the midpoint and I want to find the instantaneous speed, I take the 2 points on either side. When is 1 in the middle? 1 is in the middle only at 0 seconds and 2 seconds. So my points are going to be 0 seconds and 2 seconds. Those are just time points. They're not data coordinate points that I'm going to need for my slope. So I just go to and I figure out what the coordinate point's going to be. This one's going to be 0, 0, which means 0 seconds and 0 meters. So 0 seconds, comma 0 meters. And this one's going to be 2 seconds at 6 meters. So it's going to be 2 seconds at 6 meters. So my velocity is going to equal d sub f minus d sub I over t sub f minus t sub I. You guys probably have x sub f minus x sub I over t sub f minus t sub I. It means the exact same thing. I'm just using distance so my kids don't confuse with the x, y that they're so used to seeing in the slope equation. So this is kind of the guess method, just out of order a little bit. I plug them in. Do I have a number for v? I don't. I'll leave it the same. Do I have a d sub f? I don't know. Yes, I do, because this is going to be, again, this is t sub I, this is t sub f, this is d sub I, and this is d sub f. So it's going to be 6 meters minus 0 meters over 2 seconds minus 0 seconds. When I get done, it's going to be 3 meters per second. Now, here's the thing you need to realize. It's asking for velocity. That means you're going to have to go to your equation list, write down that equation down, and get it correct. Even if you get the wrong answer, you should still get 2 out of 3 points for attempting the problem with the correct equation and getting the correct unit. This is a memorization. That's all it is memorization. Go look at any question on your paper. Go look at any question, and if it ever says speed equals X meters per second, you know that's going to be the unit. You need to have your units memorized. Distance is always going to be in meters. Time is always going to be in seconds. Velocity and speed are going to be in meters per second. And acceleration is going to be in meters per second squared. Get that memorized. Now, find the average. So let's go to letter D. Find the average speed from 2 to 4 seconds. What is the instantaneous speed? So now we got the exact same kind of problem. Before we were told to find the instantaneous speed first. Now we're told to find the average speed. And we know that this will give us the instantaneous speed in the midpoint. Well, what's between 2 and 4? It's 3. So let's get this out of the way and let's work on this right here. It tells me my points. The points are 2 seconds and 4 seconds, comma, because we know these are going to be coordinate points. And what is 2 seconds? 2 seconds is 6, because we already have it up here, 6 meters. And what is 4? 24 meters. Now, what are my variables? I have I have a seconds. So this is my first second, so it's T sub I, T sub F, and this is my D sub I, D sub F. Now plug it into my equation for velocity. V is going to equal D sub F minus D sub I, T sub F minus T sub I. And for those who hate writing the equations, I hope you notice that, yes, I could do this in my head too. Obviously, I can do it fairly easy in my head. I know that the answer is going to be 9 meters per second. But I want the work shown so that way you, as freshmen, process a problem methodically and don't cut corners and don't make mistakes. So let's plug this in and chug along. Did I change my V? No, I don't. So I'm just leave it there. This means I'm going to have my final is 24 meters, 6 seconds. 6 meters over 4 seconds minus 2 seconds, which is going to give me 18 meters over 2 seconds, which is going to equal 9 meters per second. And so when is this the instantaneous velocity for? Well, I took over here. What's my midpoint? 3 is my midpoint. So velocity at 3 equals 9 meters per second. Let's answer the rest of these questions so we can end this video. This says, Dan rides his skateboard downhill. He starts from a stop and speeds up at a rate of 5 meters per second for 6 seconds. So my class knows what I want you to do. Don't even joke around. Don't even just waste time. Come over here and you see these numbers with units, label them immediately. So this is going to be 0.5 meters per second squared. Remember what meters per second squared was? It was an acceleration. So label that A. You know it's going to be acceleration because of the units. Again, I sound like a broken record. Get those units memorized. And then 6 seconds. Well, that's going to be time. Now, what equation do we have that asks you for distance when giving only time and acceleration? The equation D equals 1/2 AT squared. So I have my variables. A equals 0.5 meters per second squared. And T equals 6 seconds. So let's plug them into the equation. D equals 1/2 times 0.5 times, let's plug in my proper units so we're not confused, 0.5 meters per second squared times 6 seconds, and all of that is squared. Now, let's break this down. That means this is going to be D equals 1/2 times 0.5 meters per second squared times 36 seconds squared. Now, you should get a calculator and then just plug that in immediately. And I'm going to plug that into my calculator. 1/2 times 1/2 should get you 0.25 times 36. This is going to get you, now, so what distance? This is going to get you a distance. So no matter what, if you can't figure out what these units are going to be, if you don't know those seconds are going to cross out on top, we're going to cross out with these seconds on bottom to give you meters, have them memorized. Distance gives you meters. Time is in seconds. Speed or velocity is in meters per second. And acceleration is meters per second squared. This is distance, so no matter what, it's going to be in meters. So D equals something meters. Well, when I do my math, this is 9 meters. So that means while this person was speeding up, in 6 seconds, they crossed 9 meters. Now, how fast was Dan traveling at after 6 seconds, and how fast were they traveling at 10 seconds? This is a manipulation of the acceleration equation. So you're asking how fast. So how fast means velocity. You're looking for velocity. Now the acceleration equation is A equals V over T. Okay? If you're given the acceleration, you should be able to solve for V. So my acceleration is going to be, let's do the 6 second one first. 0.5 meters per second squared equals velocity, because I don't know it, at 6 seconds. So how do I do that? Well, in my class or anything, you undo what is being done to the letter you're looking for. I need to get V all by itself. Is it by itself yet? No. So I have to isolate V. So I do it by undo what's being done to V. V is being divided by 6 seconds. So how do I undo divided by 6 seconds? Well, times 6 seconds. And let me do this in a different color so we can see. So times 6 seconds and times 6 seconds, and that's going to get me, when I get done, cancel out there, and 6 times 0.5 is going to equal 3 meters per second is my velocity. How do I know that it's going to be meters per second? Well, I could show you how the units cross out, but more importantly, you need to have the units memorized. So out of my 3 possible points for this one, my work was shown, I have the correct unit, and I have the correct answer. That's 3 out of my 4 points. Now let's do the 10 seconds one. It's a manipulation of this equation again. So A equals V over T. My A is 0.5 meters per second squared. My V is my unknown. And then my T is 10 seconds. Well, it's going to be half of whatever my time is, and we know this, but let's play along anyway. So what is being done to V? It's being divided by 10, so how do I undo a division by 10 seconds? Multiply by 10 seconds, cross out. You know this is really 10 seconds over 1. Multiply by 10 seconds over 1, and that's going to equal 5 meters per second. 5 meters per second equals V. Okay, I hope this was useful to you. Again, I know this is long, but this isn't meant for you to watch in one sitting. This is meant for you to pick and choose what you need. Now, almost all of our physical science students, all of our physics first freshmen, are going to need help with the equation. That's just the truth. If you have any more questions, ask your teachers or come by and get help. Thank you.